So part 2 of this question, we're up to D. For a different species of shrimp, the flash is only produced if the light that is to be diffracted contains some wavelengths that are less than 5.2 times 10 to the minus 7 meters, which is 520 nanometers times 10 to the minus 9. That would be 520 times 10 to the minus 9, which is the same as 5.2 times 10 to the minus 7. So anyway, that's irrelevant. We're explaining this observation that any wavelengths more than 5.2 times 10 to the minus 7 meters are not observed, and that's because the angle, if you remember, you've got light coming in, you've got a diffraction grating, and the light is observed on a screen of some description. Now, in this case, if the wavelength is too high, the diffraction would be more than 90 degrees. Remember, as you increase the wavelength, you are increasing the angle. This is the angle here at which it diffracts through. So it's diffracting more than 90 degrees, which is the difference between the screen and the incident ray. Part 2, calculate the number of slits per millimeter for the hairs of this shrimp species. Now I'm going to have to go back to the previous video to draw the information out, but you're after N, which is the number of slits per millimeter, which is 1 over D, and D I'm not sure if we were given, but you can calculate D from N lambda equals D sine theta. For a diffraction grating, we can use this version of the equation because the angle is quite large, which means that the distance up here is large compared to the distance away of the screen, which means theta. We can't use a small angle approximation because theta is too big. So anyway, we would rearrange this equation to make D the subject, and we would put N in there as well. So another way to look at this is N as D equals 1 over N. So we could then rewrite this equation to be, let's use a different colour. It would be, you can work through this in a bit more detail yourself, but capital N equals sine theta over N, that's small n, lambda. Okay, and we know that theta in this case, well, if we take this, remember they have to be less than 5.2 times 10 to the minus 7. If we use that as our wavelength, so we know the wavelength. If we take n equals 1 and sine theta, theta equals 90 degrees, this actually gives us, this is because at 90 degrees we're presumably at this point beyond which, it's sort of like the critical angle, but the critical angle for, or the critical wavelength beyond which the wavelength, it goes more than 90 degrees. In any case, sine theta at sine 90 degrees is 1, n is 1, so that's 1 over 1, and then the wavelength is the only part there, so the number of slits is going to be 1 over the wavelength. And the wavelength in this case was the 5.2 times 10 to the minus 7, I think that's right. So if you put in this value here, remember that's in meters, so you would want to give a spacing of 5.2, your wavelength would be 5.2 times 10 to the minus 4, which would be the wavelength, but in the units that we're after, which is slits per millimeter, and you get something around the value of, let's just double check on my solutions, is 1900 lines per millimeter. Anyway, that's me.